So in this problem, we're going to look at how much heat is required to convert 100 grams of ice at minus 10 degrees Celsius to water at 20 degrees Celsius. Okay, so it's important for us to see a diagram of exactly what's going to take place here. So what I've done is I've just drawn my little square here, my little ice cube. So this represents ice at minus 10. And of course, it's going to increase in temperature to 0. Of course, it's still ice. It's going to begin the process of changing its state. So you have ice at 0, so the change of state is going to take place. It's called latent heat of fusion. And of course, it's going to convert your ice at 0 to water at 0 degrees Celsius. No temperature change here. There is no temperature change. Okay, make a note of that. And then, of course, when this thing changes states, you're going to have further increase of heat energy, which is going to bring your water temperature up to 20 degrees Celsius. And of course, there is a temperature change here. Okay, so let's have a look at this. I've broken this down into 3 steps. Um, in this instance, our mass, of course, in each step is 100 grams. Okay, substance, of course, is ice and water. So here, what you have is the specific heat capacity for ice, which is 2.1. And what that represents is how much heat energy, in this case 2.1 joules of heat energy to increase or to raise 1 gram of ice 1 degree Celsius. Or in this case, this is the amount of heat energy that is going to be given off when this goes from ice to water. Okay? Now, let's have a look here. So we have 100 grams. That's taken right directly from our problem. This is our constant, our specific heat capacity, 2.1 joules over grams degrees Celsius. And our delta T is 10 degrees Celsius. Final temperature, 0, subtract negative or minus 10. Um, we look at our melting process, our latent heat of fusion. Again, that is just a constant, okay? That is a constant, and in this case, it's 333 joules over grams. And what that tells us, or what that represents, is how much heat energy, 333 joules of heat energy, is required to melt 1 gram of ice. Um, so we take our 100, that's our mass. We use our constant, and we multiply them together. Okay, and this is what our formula looks like. Q is equal to m times LF. This is m. Q is equal to m times C times delta T. And of course, our third step is temperature change again, right? Delta T here. So you're going to take your mass, which is 100. Your specific heat capacity for water, in this case, is 4.18 joules over grams degrees Celsius. And that represents how much heat energy, in this case 4.18 joules, is required to raise 1 gram of water 1 degree Celsius. Our temperature change is 20 degrees Celsius, so we plug that in. When we multiply these together, we're going to have 100 times 2.1 times 10, and of course that's going to give us Q1. When we multiply those together, we get, you just give me 1 second here, 100, I guess I could have done that one in my head, eh? 100 times 2.1 times 10, and that gives us 2100, 2100. So we would say Q is equal to MC delta T, and when we multiply those together, we end up with 2100 joules. Of course, the joules cancel, or I'm sorry, the joules don't cancel, the grams cancel, and your degrees Celsius cancel. Okay? Same thing going on here. Our formula initially looks like this, M times LF, and of course, when we multiply these um, together, oops, 33 and 33,300 joules, or grams cancel in this case. And last but not least, Q is equal to MC delta T. And again, our answer is going to be expressed in joules. Grams are going to cancel. There's this guy's canceling, and our Celsius is cancel. And we end up with 100 times 4.18 times 20, and that gives us 8,360 joules. And when we add the three steps to this problem together, okay, step one, right here, step two, right here, and step three, it's Q1 plus Q2 plus Q3, the three of them together. So of course it's going to be 2,100 plus 33,300 plus 8,360 will give us 43,760 joules of heat energy. Expressing this in using the proper number of significant digits, which in this case it's going to be 2 because we have 2 here, and 4 there. We would look like 44,000 joules, or using scientific notation, 4.4 times 10 to the fourth power.